Buffer solutions resist change in pH when small quantities of acid or base are added. In this drawing, I have a beaker filled with some water, and I've shown a buffer, acetic acid and sodium acetate or acetate anion. In this case, I'm going to say that the acetic acid sodium acetate mix is my buffer solution, and that's dissolved in water in this beaker. Within the beaker, I'm going to represent acetic acid with A bonded to H, and I'm going to represent the acetate anion with the conjugate base, or A with a negative charge on it. We have thousands and thousands of these molecules in our solution, and at this point we have a 50-50 mix, so we have an equilibrium of 50% acetic acid and 50% acetate anion in our beaker, which now represents a great buffer solution. The pH of this aqueous solution is 4.76, so with an equal concentration of acetic acid and acetate anion, the pH of this solution is 4.76. If we add a strong acid or strong base to this buffer solution can resist change to that pH. Let's add a sodium hydroxide solution, so a strong base, and let's say a 3 molar sodium hydroxide solution, to our buffer solution and see what happens. When we add our sodium hydroxide solution to the buffer solution, that means that we have dropped some hydroxide anion into solution. That hydroxide anion, in this case, will immediately react with our acetic acid and deprotonate that acetic acid, forming quite a bit more of our acetate anion. So in our resulting beaker, we have deprotonated quite a bit of our acetic acid. We only have a small amount of acetic acid left, and mostly what we have is our acetate anion. Since we don't have any free hydroxide anion in solution, our pH did not jump all that much. So the pH of this solution is 6 rather than a pH of 8 to 12 based on the amount of sodium hydroxide we've added. So what happened with our buffer solution is we resisted a large change in pH after adding a small quantity of strong base to the solution. If we were to keep adding sodium hydroxide to the solution, so at this point we're adding sodium hydroxide to this solution, eventually all of our acetic acid buffer would run out. So we would deprotonate all of that acetic acid buffer, meaning that now we only have acetate anion in solution, and eventually then sodium hydroxide, so our hydroxide anion, would also be in solution. Once we get to the point where we are accumulating quite a bit of hydroxide anion, our pH is going to jump significantly. So in this case, our pH is going to be quite a bit higher. Let's say we've got, at this point, with just a couple hydroxide anions floating around in solution, we have a pH of about 10. We've shown an example where the buffer solution resisted a significant change in pH when a strong base was added. Let's look at a strong acid. So instead of sodium hydroxide deprotonating the acetic acid that we have in our buffer solution, let's use hydrochloric acid. So let's use the strong acid, hydrochloric acid. When we add hydrochloric acid to the solution, the conjugate base of our buffer solution, the acetate anion, will deprotonate the hydrochloric acid. So once we add hydrochloric acid in solution, the acetate anion will deprotonate our hydrochloric acid, making more acetic acid. So now we have a higher concentration of acetic acid in our solution and a lower concentration of our acetate anion in solution. We've dropped the pH a little bit, but not significantly. So let's say we have a pH of about 3.8 at this point. and we would have to add a little bit more hydrochloric acid to fully protonate all of our acetate anion before we would eventually get a significant drop in pH because we have an acidic solution with free H+ ions or H3O hydronium cations in solution. So this is another situation where our buffer solution resisted change in pH when a small quantity of acid or base was added. Let's take a look at this solution in more detail. We have a high concentration of acetic acid, and we have very little, if any, acetate anion in solution. This would not be considered a good buffer solution because it cannot resist change in pH if a strong acid was added to the solution. Since we have so much more of the acetic acid, this can only resist change in pH if a base is added to the solution. However, this is actually a great solution to resist change in pH if we add a strong base to the solution because we have such a high concentration of our acetic acid in solution. So in this representation, our AH is our acetic acid. We have a very high concentration of AH, which is going to resist change in pH if we add a strong base to the solution. So looking at our burette again, if we were to add a 3 molar sodium hydroxide solution to our solution, which again isn't necessarily considered a great buffer solution because it can only resist change in pH if a base is added, but adding a strong base is the perfect opportunity for this to resist change in pH for a significant period of time. So when we add our sodium hydroxide into solution, we have plenty of acid for our hydroxide anion to deprotonate. We're going to form, again, a higher concentration of our conjugate base as we keep adding our 3 molar sodium hydroxide, but we're eventually going to get back to an equal concentration of both, so back to our buffer solution. We can then keep adding sodium hydroxide until all of our acetic acid is deprotonated, and at that point then it will no longer be a buffer. But we do have a large span of a very small change in pH where a significant amount of sodium hydroxide can be added without significantly increasing the pH.